Before starting into our results for this section, let's give a little bit of motivation with a seemingly tame function. Let's say we have f of x is equal to x to the fifth minus x minus 1. It's got three terms. It's a quintic, that is, it's of degree 5. Its leading coefficient is equal to 1, so you can imagine that its curve will come up from the left, maybe wobble a little bit, and then keep going up afterwards. If you want to get something like the y-intercept, you want to find out when it crosses the y-axis, well, you'd set x equals 0, and you could very easily get that y would be equal to -1, but then what about its zeros? What about its roots? What about its x-intercept, or intercepts for that matter? It's degree 5, so you would expect there to be at least a few of them, hopefully 1, maybe up to 5. But, well, if I remove the -1 there, very, very easy to factor this into x times x to the fourth minus 1. Super easy to find the roots. If I remove the x, then the roots would just be 1, taken a bunch of times, because you'd have x to the fifth minus 1, and if I remove the x to the fifth, hey, that's linear. That's cheating. It's way too easy. But as it stands, it's not really so obvious in any way, and actually this doesn't factor either. It's probably not obvious where you'd start even if you want to try factoring, but yeah, you can't get all three of those terms, at least not very nicely, not with the methods that we have. So you might think to yourself, okay, we can't do that, but we have stuff like the quadratic formula. I've talked about the cubic formula. I've mentioned the quartic formula. Is there a quintic formula? Do we have something that we can just fall back on to spit those numbers out? But in this case, we don't get that either. As of the 18th century, trying to figure out problems like this, trying to figure out when a function like this, a quintic, was equal to 0, is a topic of some interest for mathematicians, in particular mathematicians in budding fields of modern analysis and modern algebra, where they want to figure out not just how you could find the roots of something like that in particular, but something a bit more general, something of degree 5 overall, or even higher degree. Whereas they were working on these sorts of things, people like Gauss, we've seen him a few times, he was pretty good at this stuff, but even he had to admit that there is little doubt that this problem does not so much defy modern methods of analysis as that it proposes the impossible, which he said in 1798. And over the next 35 years, a bunch more mathematicians would take their cracks at this problem, but three in particular made good progress here. The three being Ruffini, who we mentioned before, along with Abel, and somewhat independently, a different young mathematician by the name of Galois, where as they would look at this, they would be able to more concretely prove Gauss's thought correct, that for quintics this was impossible, and actually for anything more than a quintic, you can't find a closed, repeatable formula for any polynomial of any such degree. There doesn't exist one for such things. And somewhat interestingly, even though Abel and Ruffini would have their proof together by 1824, and Galois wouldn't put his ideas together until 1830, where they would actually get rejected in 1831 for being a little bit too loose. Today, when we're talking about this sort of thing, most mathematicians actually use Galois' ideas, the ideas that he had for working through this sort of thing. They were actually published posthumously. Galois died in a duel in only a few years later. He died at 20, and the results were published in 1846, along with some other results, where his thoughts would come to be known as Galois theory, which is math way, way, way beyond the scope of this class, into topics of modern and abstract algebra that honestly do scare me a little bit, so we're not going to see anything like that, but it is good context here to understand that problems like this, even for the very best mathematicians to have ever lived, not always easy, not always obvious, and sometimes not even really possible. Where what we can do instead, what we can try and do, is try and figure out what could possibly happen in here, whether we have any nice options to figure out what could go wrong, what could happen. Things like the intermediate value theorem could help us get some sense of if there are zeros. And we're going to see that we have more options here with things like the rational zero theorem, which says that if we have a rational root, that is, if we have a root of form p over q, it can be represented as a fraction, then it must be of the form that p is a factor of the constant, the last coefficient, a0, and q is a factor of the first coefficient, an. You have to have both of those things to get a rational zero. And let's be careful about this, because you look at that, you might think to yourself, okay, great, we can get any zero that way, but thinking about this guy, that would tell us that if we have a rational root, the value p has to be a factor of -1, which is just plus or minus 1, and that q has to be a factor of +1, which is again just plus or minus 1. So that would tell us that the rational roots here have to be plus or minus 1, and those, if you plug them in there, are not roots of that equation. If you plug in 1, you'd get 1 minus 1 minus 1, which is -1. If you plug in -1, you'd get -1 plus negative, or -1 plus 1 minus 1 again, so you'd still get -1. Neither works. This doesn't actually tell us if we have roots. It doesn't tell us if we have rational roots. It only says that should we have rational roots, they have to fit this kind of pattern. If we don't have rational roots, like in this case, it actually doesn't tell us anything. But if we've got nothing to work from, and we have a polynomial that we want to get some ideas for, something like this, we can use the rational root theorem or the rational zero theorem to at least get started. And we'll take an example here, another example here, to get some sense of what it is we might be looking for. So for this example, we want to list all the possible rational zeros of 3x to the fifth plus 4x squared minus 4. So what we need to do here is identify the potential factors of 3 and 4, where remember that we have q is stacked onto an, and p is stacked onto a0. Which means that what we're going to end up having is that p has to be in terms of factors of 4. So that means p has to work in terms of plus or minus 1, plus or minus 2, or plus or minus 4, while q works similarly in terms of 3, so plus or minus 1, plus or minus 3. Which means that if we want to describe the potential rational roots here, the potential rational zeros, we have the factors of -4 over the factors of 3, which would be plus or minus 1, plus or minus 2, plus or minus 4 over plus or minus 1, plus or minus 3. And that gives us the options of plus or minus 1, plus or minus 2, plus or minus 4 in terms of being over 1, and then plus or minus 1/3, plus or minus 2/3, or plus or minus 4/3 in terms of being over 3. And that tells us the general shape of what we could possibly shoot for. If we want to check to see if any of them are valid, we would just plug them in and go from there. Where, like I said, the rational zero theorem doesn't say that we definitely have zeros of these form, or that all of the zeros have to be in this form. It just gives us some guesses. It gives us places that we can start if we need to find some zeros. So let's take one more example here where we actually try and use this to get zeros.